Let me start the record. Okay, now it started. Okay, now all of you okay, type in the chat box. Have you seen both the videos? Again, effectively, I will be having only 49 students. Okay, I don't know. Okay, how about the remaining? And maybe one or two of you might have logged in two different systems. Then it is still less in number. So of course, I will not have any problem. Only thing is that you will face a lot of difficulty when you are facing any quizzes or tests. Okay, most of you have seen the videos. Maybe that will make my uh, lecture easy so that you can able to understand the concept of amplification effectively. Sai, have you seen the video?
Yes, sir.
Both of them? Simulation as
Sir,
well as the theory part of it. Okay, let
yes,
us
sir.
just go by that. So our aim is to amplify an AC signal. AC signal need to be amplified. So you have an amplifier. You have an amplifier, of course. So you need to have an signal with voltage value increased. So this is what I want. So voltage amplitude of the output signal should be more compared to the input AC signal. For that I'll be using the MOSFET. So MOSFET is used as active device. You might have heard of active and passive devices. So passive is one which will actually dissipate the power. It will not actually make any enhancement in the signal. It will only consume the power, and what will happen is it will actually reduce the reduce the signal amplitude. So we call them as passive. Active elements are one which can amplify or enhance the signal, but this active element will be actually increasing the amplitude of AC signal at the cost of DC, because we know that energy cannot be created or destroyed. You cannot increase the amplitude of AC signal without any cost. The cost involved here is, so you are actually utilizing the DC signal to amplify the AC signal, for which I want to have an active element. The active element in this case is MOSFET. In this case is MOSFET. Of course, MOSFET alone cannot amplify the signal. So let us see if I have a signal. Let me just take a signal of amplitude 10 millivolt. Sai.
Sir,
So I have an AC signal of very small amplitude of 10
10
millivolt.
millivolt.
Let me assume the frequency of this is 20 kilohertz. Make sure that there is
Yes,
no
sir.
noise from your side, man. Why that noise comes? Because many students are listening you, and then okay, this is a sine wave of amplitude. This is what I have. This is 10 millivolt. This frequency is 1 over 20 kilohertz. So this is what is the time period. Time period is 1 over 20. The frequency is 20 kilohertz. Now this has to be amplified using a MOSFET. Assume that I'll use a MOSFET directly. Is the noise from your side or someone else?
Sir, I'm using earphones, sir. Nobody is there in
No.
the room.
Where is the noise coming from? Is it from your side? Okay, let me just mute all and then you unmute yourself. Now you unmute. Sai?
Okay, sir.
Okay, now fine. Suppose if I use something like this now. So this is my MOSFET. So let me use something like this here. 1.8 volt, and then assume that this is okay. This is, let me take it as 1 kilo. What will happen, Sai? Suppose if this is the signal.
Sir, we should short independent voltage, sir.
You should short circuit.
Short circuit all independent voltage, VG and VD.
No.
VDD.
We'll go to that first. We'll go to that later. The point is, will this amplify?
Yes,
No,
sir.
sir.
Will this amplify? Now I'm having a 10 millivolt sine wave applied to a MOSFET this way, and I'm having a 1 kilo ohm resistor and there is a 1.8 volt, and assume that there is a WBL given, so this WBL is equivalent to like 10, ratio is 10. Will it amplify the
Yes, sir.
signal? Will it? Okay,
Yes, sir.
first of all we'll see whether the MOSFET is in on condition or off condition. Assume that okay, this has got VTH is equal to 0.4 volt and Kp is equal to 200 microampere per volt square. All those stuff is there. Now the question is the MOSFET on in this particular case? Is it on? Is it on or off? Okay, when does the MOSFET turns on?
Sir, VG is greater than VTH.
When VGS is greater than VTH, then only MOSFET turns on. So here
Yes,
VTH
sir.
is 400 millivolt. How much is
Yes, sir.
gate voltage you applied?
10 millivolts.
So it is the MOSFET on or off?
Off.
Off. So there is no question of amplification at all. No amplification. We thought of
Yes, sir.
applying a AC signal to an amplifier which is consisting of a MOSFET. Can you see there is a MOSFET?
Yes, sir.
There is a MOSFET, there is a AC signal, you are looking at the output voltage, you are looking at the output voltage V0. You are looking at the output voltage V0. But you're not getting the amplification because, of course, forget about amplification,
MOSFET is
your
off.
MOSFET itself is off. Correct? We need to
Yes,
do
sir.
something. We need to do something. So, is it like, okay, how does your input characteristics, sorry, transfer characteristics of your MOSFET looks like? Is it this?
Yes, sir. ID versus
Will it go
VG.
like this? This is VTH. Suppose if I apply this signal as it is, so is it operating here?
Yes, sir.
Is a MOSFET on or off?
Off.
Off. So where I should apply this? Where should I apply this? If at all if I want to consider this as a valid signal, I cannot apply this AC signal. I cannot apply this AC signal at this voltage. I need to apply somewhere here. Correct? Suppose
Yes, sir.
what I'll do, I'll apply here. What do you mean by applying here? The voltage,
Sir.
you can see this is your 0. This is your 0. So can you see here? This is 0 volt, and over and above that amplitude is varying. Can you see here? This is 0.
Yes,
This
sir.
will go up to 10 millivolt. So VGS goes up to 10 millivolt and it goes up to minus 10 millivolt. You can see the entire MOSFET is off with voltage 10 millivolt or minus 10 millivolt. Correct?
Yes, sir.
What I should do now? Suppose if I shift this from here to here. Now assume
Sir,
that this is
we should
0.6. Assume that this voltage is 0.6. Is this
6.
0.601 volt?
Yes, sir.
Because amplitude is 10 millivolt. You are already there at 600 millivolt. 600, sorry, this is 610. Is it 610 millivolt? Is it 590 millivolt? Sorry, this is 0.61 volt and this is 0.59 volt. Am I correct?
Yes, sir.
Now, what I'm trying to emphasis here is that instead of applying the signal this way, instead of applying the signal at 10 millivolt without any DC shift, I should apply the same 10 millivolt with some DC shift. If I don't apply the DC shift, MOSFET is always off. How do I provide the DC shift? I have to make sure
Sir.
that this signal is shifted up. How do I do that?
Sir, we should provide another DC source at VG.
Yeah, what you can do is, that's what is called as biasing. See, now I'm just providing this. So I'll make this as, this is 1.8. No, let us make it as 200k. This as 100k. Correct?
Yes, sir.
What is the voltage? Forget about this now. What is the voltage at this point because of this 1.8? What is the voltage at this point? Is it 0.6? It is 0.6 volts. So 1.8 into 100k by 300k will become 0.6 volts. Correct?
Yes, sir. 0.6.
That means am I here?
Yes, sir.
Am I here at 0.6? Corresponding
Yes,
to
sir.
that, will I have some DC current ID flowing through this MOSFET?
Yes, sir.
Correct? Now, over and above this, I'll apply this. You can see around that 0.6, I'm applying this. Now,
Yes, sir.
what is the signal that you have here? Okay, what I'll do, I'll put a capacitor. What is the purpose of this capacitor? What is the purpose of this capacitor? Last class we discussed.
Sir,
Purpose. Hey, what is this sound, man, from your side? Okay, somebody is making noise.
It will avoid DC backlog, and it will block the DC voltage and allows only AC source.
Meaning, it couples the AC signal. It will not alter the DC voltage of 0.6 what we fixed using this 200k and 100k. So this is used to couple only the AC signal. Why it couples AC signal? We discussed in the last class. It acts like a short circuit because the reactance offered by the capacitor for high frequency signal is low. Am I correct?
yes, sir.
Sai, you just mute yourself. I'll take some other student. So no, lot of noise from your side. I can't just take this. Hanuman Sagar, Sandeep. Sandeep. Sandeep, unmute.
I am.
Okay, Sandeep.
Yes, sir.
Have the mic close to you.
Yes, sir.
Still,
Now, sir.
still closer.
Hello.
Okay, fine. Be loud, man. I
Yes,
can't
sir.
hear you properly. Okay, now the point is we are applying a AC signal with some DC shift. Now, am I effectively applying the signal somewhere here like this? Am I correct? Hello.
Yes, sir.
Okay, now when there was no AC signal, what was the current flowing? When there was no AC signal, what was the current flowing? Was the current flowing to the drain? Was it equal to half Kp, as long as the MOSFET is in saturation? Is it half Kp W by L VGS minus VTO whole square? Is this the current? When there
Yes,
was
sir.
no AC voltage?
Yes, sir.
Correct?
Yes, sir.
Be loud, man.
Yes, sir.
Okay, now what what I have now is this is only when there is no AC, when there is no AC signal. With AC signal, does this change now? So when there was no AC signal, was it exactly only 600 millivolt?
Yes, sir.
Now when you apply the AC, when you apply the AC signal, does this 600 millivolt plus one sine wave of 10 millivolt? Am I correct?
Yes, sir.
So is it something like this? 0 and then you have 600 millivolt as the reference, and over and above that, do you have something like this now?
Yes, sir.
Correct? Now what is this? Okay, now you have this. Correct? Is this your small v capital GS?
Yes, sir.
This is small signal plus the DC voltage. Small signal plus the DC voltage. Now ಕಟ್ಲಿ ಮಾಡಲಿ ಆಮೇಲೆ ಕಟ್ಟಿಸಿ ನಾವು ಕೈ ಕಟ್ಸಂಗ್ ಕಟ್ಸಿ. Okay, now we can see now it is becoming so difficult to analyze this. Am I correct? Because you have this 600 millivolt, you have this, all those things. Now whenever you have a transistor being used for an amplifier, we need to write its model, AC equivalent model. Getting the point? I need to represent this MOSFET by a model. How many of you seen Taj Mahal? Just type in chat box. How many of you have seen Taj Mahal? I think maybe very few in number. So the number of students who have seen Taj Mahal, just put in chat box. No, I just want to relate it to a model. Type in chat box. Okay, how many of you seen Taj Mahal? I'm not getting any answers. Yes, sir. Okay, there are few yes. Good. All are yes. Put in chat box. Am I audible? No, sir. No, sir. Make it fast. Yes, no, yes, no. Hello. Okay, now we can see there are so many no's. Let me just ask one more question. How many of you seen the Taj Mahal model that was displayed in Tumkur? Somewhere there was exhibition, no, of Taj Mahal. How many of you seen that Taj Mahal? The first Taj Mahal is the actual Taj Mahal. The other one is the model Taj Mahal, which was there put up in one of the exhibition. I think you can see most of you have seen that Taj Mahal, which was, of course, there are few no's also because we not Tumkurian. Okay, of course, the point here is what I'm trying to show here is the one which was displayed in Tumkur was actually a model of Taj Mahal, which is the actual Taj Mahal at Agra. Correct. Now the point is, was it looking almost similar to that of the original Taj Mahal? It was. Who is there with me? Hanuma
Yes,
Sagar.
sir.
Hanuma
Yes,
Sagar,
sir.
are you from Tumkur?
No, sir.
Anybody from Tumkur can just log in. Okay, unmute yourself and then who have seen that Taj Mahal? One of you. Make it fast. I don't have too much time because I want to relate to that. Rupashri, you said yes. Why don't you unmute? Hello.
Sir.
Okay. Now you can
Hello,
see.
sir.
Fine. Uh,
Yes, sir.
in that model of Taj Mahal, could you able to see so many pillars which was similar to that of the actual Agra Taj Mahal? There were pillars on either
Yes,
side.
sir.
Okay.
But I have seen the actual Taj Mahal.
No, you might have seen in the photos, no?
Yeah, yes, sir.
You
Yes,
have
sir.
seen in the photos. It was almost replicating.
Yes,
It
sir.
was almost replicating, meaning that we represent the Taj Mahal using a model so that it resembles how does the Taj Mahal looks like. Now the point here is, now I want to model a MOSFET. I want to model a MOSFET. This MOSFET model
Yes,
should
sir.
represent the working of the MOSFET for that AC signal. Now,
Yes, sir.
you know that I want to create a MOSFET. So the MOSFET is this. This is a MOSFET symbol. This is a MOSFET symbol. Now we are trying to analyze. Okay, how does this will act like an amplifier? Now we are struggling to get, okay, what is this? What is this? All those things. Now instead of having this MOSFET as it is, I will create a model of the MOSFET. So when I say model, it should represent the working of this MOSFET, but in a different way. Even though you're not actually gone to Agra and then saw the what is that Taj Mahal, you could still have
Taj
some
Mahal.
photos. You could still have some photos where at the background you have a Taj Mahal, which is a model. Am I correct?
Yes, sir.
Now what we'll do is we will try to mimic the same thing. Let me not have this MOSFET. Let me have a model of the MOSFET. Let me have a model of the MOSFET so that I can analyze the amplification of the AC signal using that model instead of the actual MOSFET itself. Because we know that Agra is too far from here, maybe around 2000 to 2.5 kilometer away from us. Instead of that, we can just go hardly 2 to 3 kilometers from our house, and then we can have a photo with the Taj Mahal. Now we'll do the same thing here. Let us not take this complicated MOSFET for analysis. We will take a model of this MOSFET and try to analyze. Try to analyze that working of the MOSFET so that we can able to understand the working of MOSFET as an amplifier. Now, as it was said here, was there any current flowing due to this VGS here? Was there any current flowing through this because of this VGS? Was there any current flowing here? Hello?
Yes, sir. For 0.6 volt.
For 0.6 volt, there was a current flowing.
Yes, sir.
Now,
There was a current.
suppose if I change this 0.6 to 0.66, does the current change?
Yes, sir.
Where you are actually changing the voltage? Suppose if you take this MOSFET, where you are changing the voltage?
At gate
At
voltage.
gate you are changing, at drain it is
Gate
changing.
to source.
At gate you are changing the voltage, at the drain the current is changing. Can you see
Yes,
this
sir.
is something like there are two parameters, one is voltage, other is current, which is one is at the input and other is the output
Other
point.
is the output.
So can you see there is something depending on something else? What is depending on what?
Transfer characteristics.
What is depending on what?
Current is dependent on voltage.
Current is depending on voltage. Shall we represent this as a voltage dependent current source?
Yes, sir.
This is a current source.
Voltage dependent current source.
No. This current source depends on voltage. Am I correct?
Yes, sir.
This is a current source which depends on voltage. It depends on
Yes,
what
sir.
voltage? VGS.
Input voltage.
Input
VGS,
voltage
sir.
VGS. So we will write the ID, which is a function of VGS. Now,
Yes.
if there is a change in del of VGS and del of ID, for any change in VGS, will there be any change in ID?
Yes, sir.
So usually what you write resistance as?
V is equal to I. Yes, sir. V by I.
R is equal to V by I. Similarly, what you write
Yes.
what conductance as?
Conductance 1 by R. If I'm not sure.
This one. Okay, 1 by R or I by V.
Yes, sir.
Correct? Suppose if current and voltages are corresponding to one side. Suppose if it is assume that this is also input, this is also input. Shall we call it as input conductance?
Yes, sir.
Because if both the parameters are related to input side, I will call it as input conductance. If it is related to output side,
It is output conductance.
output conductance. But here you can see one is related to output, the other is related to input. What shall I call this as?
Transfer conductance.
Transconductance. Fine. Okay,
Trans
transfer conductance. We call it as a new word, transconductance.
conductance.
So transconductance is a parameter which relates output current and input voltage. It's not conductance, it is transconductance. It is certainly a conductance parameter because it is I by V. Why it is called as trans is because you are relating output current and input voltage. Input voltage. Now, what we'll do is we will represent this MOSFET uh, as a transconductance parameter. So what I'll do is, because it will take maybe one more class to understand this MOSFET. Okay, MOSFET as an amplifier. Afterwards, it is just a cakewalk for all of you. Now we can see this is what you have. Let us assume that this is VGS. Okay, this is VGG. Let me call it as this is VGS1. Let me call it as this is VGS. Corresponding to this, I have an ID. Correct. Now,
Yes, sir.
can you see there is a slope? If you take a tangent
Yes,
at that point, so suppose if I take this as is this ID by VGS1 at that particular
Yes,
point,
sir.
I will call this as
Slow.
GM. So this
Yes,
is
sir.
GM. Suppose over and above this, if you apply something like this here, what is this here? This is capital VGS, like 0.6.
Yes, sir.
And over and above this, you have 10 millivolt above and 10 millivolt below. So will it become 0.61 volt and 0.59 volt?
Yes,
Because
sir.
you are actually varying about that 0.6. This is 0.6, goes up to 610, comes back to 600 millivolt, goes down to 590 millivolt, and then it keep on varying like this. Correct? Now, did you had some value of ID for that 0.6 earlier
Yes, sir.
because of this slope? When you
Yes,
apply
sir.
more voltage corresponding to this, do you have more current? See here,
Yes, sir.
when your effective VGS increases because of the applied small signal, Does your current also varies due to this characteristics of your what is that MOSFET? Now, does this current is keep on changing as you vary the voltage small VGS?
Yes,
There
sir.
was a capital VGS. What is this capital VGS?
It is gate to source voltage. Actual.
DC voltage.
Yes,
Say
sir.
it as
Okay,
DC
sir.
voltage. DC voltage is 600. What is this small VGS?
It is DC plus
No,
that
no, no, no,
AC
no, no, no.
signal.
Just small VGS is only this 10 millivolt signal.
Okay,
I'm just
sir.
taking only. So overall, this is small v capital GS.
Yes, sir.
Correct. Now, what I want to convince you people here is that because of this applied small signal, what is the change in current? What is the change in current? Now, what I'll do is before I go to that. So, can you see the structure of MOSFET? Is the structure of MOSFET something like this? This is P minus, this is N plus,
N plus.
gate, this is MOS, correct?
Yes, sir.
Now, in this, will you apply VGS here?
Yes, sir.
What is the current that will flow here? So, what is this here? You have a metal oxide semiconductor. What is the property
Yes.
of oxide? Oxide.
Oxide.
Oxide is an insulator.
Yes, sir. Yes, sir.
Insulator means the current
Which does not allow current to pass through
current
it.
is zero, so that resistance is infinite.
Yes, sir.
So no current flows. So if you look from the gate side, suppose if you look from the gate side, how much is the resistance you are seeing?
Yes, sir.
How much is the resistance you are seeing? Now you are looking into the gate. This is your gate, no?
It is
You apply
infinity.
your VGS here. How much is the resistance you see here? This one,
Infinity.
infinity. How do you represent infinite resistance? How do
1
you
by 0.
how do you represent? Now shall I
That.
represent it by an open circuit?
Okay, sir.
Open circuit is infinite resistance, no?
Yes, sir. Yes, sir.
So the MOSFET which was there, now I'm trying to create a model for that. That model is the input, that is gate source. This is gate source is now represented by open circuit. You can see now we are trying to represent the model of Taj Mahal in Tumkur now. Now we are trying to represent the MOSFET symbol, or of course when you are representing something, it should have some significance. You cannot simply represent it by whatever you want. So it should exactly replicate the working of that MOSFET. So does this open circuit for your MOSFET, is it true here also?
Yes, sir.
Why it is true?
Because before that also gate and source were not shorted.
No, there was no current going to the gate terminal. Same thing is represented here.
Yes, sir.
Now instead of writing this symbol, if I write this, it is one and the same. If I
Yes,
write
sir.
like
Yes.
this, I can easily analyze. If I write like this, my analysis is difficult. So in order to ease my analysis, I am representing the MOSFET at the input side by a open circuit, which is exactly the thing here. Now
Yes, sir.
you have a drain, you have a source. Now if at all, if you apply some signal, what is the impact of this signal on the drain side? What was the
Sir,
impact
once
of?
again, sir.
Yeah. Now the point is, what is the impact of applying signal at the gate onto the drain side? Will it impact on change in the current?
Yes, I
This
mean,
is applied voltage. Will it have a change in current here as per the slope? If it increases, current also increases.
yes, sir.
If this reduces, current also reduces. Now
Yes, sir.
that is represented by what? So shall I say this as can I represent between drain and source, a, okay, let me just do it this way. This is what? GM into VGS. This is drain, this is source. So what is this now? This is the symbol. Of course, you might have heard of. I think maybe it is not yet started in your networks. This is a current source. So I think you already know
Yes.
this current source. This is
Yes,
an
sir.
independent current source. If it is a dependent current source, I will write it as a rhombus.
Yes, sir.
So now this is a dependent current source, GM into VGS. So what is this GM into VGS? What is the GM parameter?
It is conductance.
It is transconductance.
Transconductance.
So this transconductance is due to the capital VGS and the corresponding capital ID. Correct?
Yes, sir.
So this capital this small gm, you can change it by changing the value of this VGS. Instead of 0.6, if you make it 0.7, the GM will change, because ID and VGS will change, your GM will change. Correct?
Yes, sir.
Now what we are trying to represent now is whatever circuit you had in the form of this was VDD, no? RD, this is R1, this is R2, this is CC, this is V in, this is V out. Correct?
Yes, sir.
Now let me replace this by the equivalent model. I will replace only this. How do I represent that MOSFET as? This is, we know this is drain, this is gate, this is source. Correct?
Yes, sir.
So I will write this is gate, this is source, this is drain. What is this? GM into
Drain.
VGS. This you can see,
VGS.
this is gate. So gate, drain, source. What is connected to drain here?
Drain.
What is
VD.
connected? Here.
Resistance. R D.
Correct? What is
Yes,
connected
sir.
to gate?
R1 and R2.
This is R1. And okay, what I'll do, I'll just do this way. This is R2, this is R1. Is this connected here? Correct?
RD. Yes, sir.
Is this grounded? How about this? This is this way, and this is this.
Ground. Yes, sir.
Correct?
Yes, sir.
Looks complicated. Is it?
No, sir. Source and R2 are connected or what, sir?
No, they are not connected. They are not connected. It's simply going down here. It's not connected. So it's not connected here, no? This is ground, this is ground. These two are connected,
Yes, sir.
but it is not
Yes, sir.
connected here. When you have this same symbol here, this all are shorted here. As it is done here, this and this, they are all shorted. Correct?
Yes, sir.
Now this is the representation of MOSFET by its model. Only this is the change I made.
Yes,
Correct?
sir.
But I want to write an EC equivalent circuit for the entire amplifier. So for small signal AC equivalent circuit.
Yes, sir.
So now, what do you mean by small signal?
Which frequency is less?
Which varies. Am I correct? Which
Yes,
varies.
sir.
So now the question is, does this DC voltage of 1.8, will it be constant or will it be varying?
It will be constant.
So constant. So there is no variation. So
No, sir.
even though this is 10 millivolt, you can see there is a variation. Even though it is 1.8 volt, but it is constant. Am I correct? It is 1.8,
Yes, sir.
it is constant. So with respect to this 10 millivolt, will it look like constant?
Yes, sir.
I am just looking in terms of variation wise. So there is no variation. Correct?
Yes, sir.
So you remove all DC sources for what I'm trying to say is, so in order to write the AC small signal analysis equivalent circuit, you short all DC sources. So what I'll do, I will short this. This is no more represented as VDD, but I am represented as a short. Why I am shorting? Because it is
In
not
order to
yeah.
have all AC signals.
No. This whatever DC signal you have, since it doesn't have any variation, I will treat it as short circuit for my AC signal analysis. I'm treating.
Okay, sir.
So I will going to treat all DC sources which have constant amplitude as short circuit for my AC signal analysis. So I have shorted. Correct?
Yes, sir.
The moment I short, does this potential become same as this potential?
Yes, sir.
So does the circuit looks slightly different now? Now let us also see what is the reactance offered with this capacitor for higher frequencies.
Shorted.
Will it be
Shorted.
very less in terms of reactance? Will it be very less reactance?
Yes, sir.
Okay, what do you mean by very less reactance? Shall I short this also?
Yes, sir.
So I will represent all capacitors by a short circuit for my AC signal small signal AC analysis, and the DC sources by short. So
Yes,
when I'm
sir.
representing this short, this also a short, can you see the circuit becomes so simple?
Yes,
This
sir.
is grounded, this is also grounded, this is gate, this is source, this is GM into VGS, and this is grounded.
RD.
RD, R2, R1, this is V in, this I call it as VGS. Am I correct? GM into VGS.
VGS.
Correct?
Yes, sir.
I can rewrite this more specifically. Now this looks okay, bit confusing. I will write this way. This is R1, this is R2, this is gate, this is source, this is GM into VGS, and this becomes RD. This is V0, this is V in, this is VGS plus R1, R2, RD. Is it same as this?
Mm,
Are these two same?
Ground.
Okay, I'll ground it. Are they same?
Yes.
They're perfect. Now you
I
can see.
can't see both.
You can't see this?
Both I can't see, sir.
I'll just show you both.
RD. Yes, sir.
You can see R1, R2 is there as it is, but gate to ground. R1 was there between gate and ground here. I just swapped it. I just pulled it down here, and this I pulled it down here.
Yes, sir.
So when you pull it down, it is R1, R2 parallel. When you pull it down here, this RD comes down here. And this was your V0. This was your V0. You can see I'm getting the same V0 here. This is the AC equivalent circuit of this complicated amplifier. See, this
Yes,
is the
sir.
circuit. I have shorted this, I shorted this. So when I short ground, this will flip, this will come down here. The MOSFET, you are representing it by open circuit and a current dependent, voltage dependent current source. So this is MOSFET, this is because of shorting, and this is because making the DC voltages go. Fine?
Yes, sir.
Yeah, so try to understand how to write the small signal AC equivalent circuit of any amplifier, then you are almost 90% done with the analysis. 90% done with the analysis. We didn't do anything great here. So we had the circuit, we shorted this. The purpose of shorting is, even though it has got large amplitude, since there is no variation, we treat it as short circuit for AC signal. We say it as AC shorted, AC shorted. So AC equivalent of this is a short, and again AC equivalent of this is a short because it acts like a what, zero resistance, because XC will be very small if the frequency is more, because you are looking at an AC signal which is high frequency signal. You treat it as short circuit, so you short all capacitors and you short all DC sources. You retain your AC source as it is. So I'm retaining the AC source as it is. Okay, we will analyze the amplifier in the coming classes. Thank you so much.
Yes, sir.
Yeah, let me just scroll through. Don't leave the class. I just scroll through the attendance. Okay, just 1 second. Okay, I'm done. Thank you.